In the vast expanse of the cosmos, a mystery lurks: dark matter. This elusive entity, although invisible, exerts a gravitational pull that holds our universe together. It's like a cosmic glue, binding galaxies, shaping the large-scale structure of the universe. Yet, despite its profound influence, dark matter remains shrouded in mystery. We can't see it, we can't touch it, and we can't detect it with our current instruments. It's as if we're chasing a ghost. But what we do know is that it's out there, making up about 80% of the matter in the universe. And yet the question remains, what exactly is dark matter made of? Scientists have proposed numerous candidates, from exotic particles to undiscovered dimensions. But today, let's delve into a particularly intriguing possibility. So, what if this mysterious dark matter is made of something equally mystifying? Primordial black holes. Before diving into the heart of the matter, it's essential to understand what we currently know about dark matter. Dark matter is a hypothetical form of matter, unseen but thought to make up about 85% of the matter in the universe. It's invisible because it doesn't interact with light or any other form of electromagnetic radiation. But we know it's there because we can see its gravitational effects on galaxies and cosmic structures. Dark matter's presence is inferred through its gravitational pull on visible matter, bending of light around massive objects, and the way galaxies rotate. We see galaxies spinning so fast that they should tear themselves apart, yet they don't. Something unseen must be holding them together, and we call this dark matter. Current theories suggest that dark matter is made up of exotic particles that we have yet to detect. These particles are thought to be cold, meaning they move slowly compared to the speed of light, which allows them to clump together and form the large-scale structures we see in the universe. However, despite decades of searching, we've yet to find direct evidence of these particles. We've built detectors deep underground to capture a glimpse of these elusive particles, and so far they've come up empty. This has led some scientists to consider alternative explanations. One such proposition is that dark matter could be made up of primordial black holes. Unlike the black holes that form from collapsing stars, these primordial black holes are theorized to have formed in the first fractions of a second after the Big Bang. To fully appreciate this notion, it's crucial to remember that our understanding of dark matter is evolving. It's a puzzle that scientists are actively trying to solve, with each new piece of data adding to our knowledge and shaping our theories. Despite our advances, the true nature of dark matter remains elusive. But with every passing day, we inch closer to unraveling one of the greatest mysteries of the cosmos, the enigma of dark matter. Enter the primordial black holes, a new contender in the search for dark matter. These aren't your everyday black holes, the kind that form from the collapse of massive stars. No, these are a different breed altogether, born in the tumultuous moments following the Big Bang itself, the primordial black holes. Now you might be wondering, what sets these primordial black holes apart from their stellar counterparts? Well, unlike stellar black holes, primordial black holes are thought to have formed directly from density fluctuations in the early universe. They didn't need a star to give them life. Instead, they emerged from the primordial soup of particles that filled the universe in its infancy. But why are we even considering these primordial black holes as a candidate for dark matter? Well, it turns out that these early universe relics could have just the right properties to explain the elusive dark matter. They don't emit light, they're incredibly dense, and, most importantly, their gravitational effects could account for the strange cosmic phenomena we attribute to dark matter. The size of these primordial black holes is another interesting point of discussion. They could range from the size of an atomic particle to the size of 1,000 suns. That's a massive range, isn't it? Well, this is where things get even more intriguing. The smaller these black holes, the more of them there would need to be to account for the dark matter. The concept of primordial black holes as dark matter is still a hypothesis, a theory. It's yet to be proven. But the beauty of science lies in its relentless pursuit of truth. Scientists all over the world are working tirelessly to gather evidence, to test this hypothesis, to unlock the secrets of the universe. Could these primordial black holes be the key to solving the dark matter mystery? Well, the jury is still out on that one. But one thing is for sure, the quest for understanding dark matter is taking us on a fascinating journey, one that's redefining our understanding of the universe and our place in it. Looking for evidence of primordial black holes, we turn to a phenomenon known as gravitational microlensing. This cosmic marvel happens when a smaller object, like a primordial black hole, passes between us and a distant star. The black hole's gravity bends the star's light, causing it to brighten momentarily. This brief, one-time flash is a microlensing event. Microlensing is like a cosmic magnifying glass. It gives us a chance to spot these black holes that might otherwise remain hidden in the vast expanse of the universe. The beauty of it is that it doesn't rely on the black hole emitting any light or radiation. Instead, we merely observe the effects of its gravity on the light from a star behind it. Importantly, microlensing can help us estimate the mass of the object causing the event, so it's a valuable tool for detecting primordial black holes and determining if they could be the elusive dark matter. While microlensing offers a promising detection method, it's not the only tool in our arsenal. From the cosmic microwave background to the structures of galaxies, the universe might be bearing the fingerprints of primordial black holes. The cosmic microwave background, or CMB, is the oldest light in our universe. It's like a snapshot of what the universe looked like around 380,000 years after the Big Bang. It's a faint cosmic glow, filling all space, that gives us a unique view of the early universe before stars and galaxies formed. Now imagine if primordial black holes, as dark matter, could leave an imprint on this ancient light. How, you may ask? When high-energy particles interact with the CMB, they can leave tiny distortions or bruises. If primordial black holes are indeed a significant component of dark matter, their interactions with the early universe could potentially cause such distortions. Moving from the cosmic to the galactic, let's consider the structure of galaxies themselves. Astrophysicists have long puzzled over why galaxies form and rotate the way they do. The presence of dark matter has been the leading explanation, providing the extra gravitational pull needed to hold these massive structures together. If primordial black holes make up dark matter, their distribution and clustering could explain the observed galactic structures and cosmic large-scale patterns. They could be the invisible architects, shaping galaxies and driving their rotations. But it's not just about the large-scale structures. Primordial black holes could also influence the formation of smaller cosmic bodies. For instance, if a primordial black hole passed through a protoplanetary disk, the disk's material could accrete onto the black hole, leading to the formation of planet-sized objects. Yet, the primordial black hole hypothesis is not without its challenges. For one, the imprints on the CMB are yet to be definitively detected. Also, the distribution of primordial black holes would need to be just right. Too many, and they would disrupt galactic structures rather than explain them. In the end, what we have is a tantalizing possibility, a new way to look at old mysteries. It's a reminder that in the realm of cosmic exploration, there's always more to discover and understand. Opening. As compelling as the primordial black hole hypothesis might be, it faces significant constraints and challenges. There are hurdles to cross before we can confidently declare primordial black holes as the elusive dark matter we've been seeking. One of the key challenges lies in the realm of observational evidence. For instance, gravitational microlensing observations have so far failed to detect a sufficient number of primordial black holes, causing some to question whether they exist in the quantities necessary to account for all dark matter. Moreover, the existence of primordial black holes in large numbers might conflict with other astrophysical phenomena. For example, they could disrupt the stability of stars in binary systems or affect the distribution of matter in galaxies in ways we have not yet observed. Yet it's important to remember that science is a dynamic process, constantly evolving with every new observation and experiment. Despite these challenges, The primordial black hole hypothesis continues to be a tantalizing prospect, stimulating a wealth of research and debate. While primordial black holes are fascinating, they are not the only game in town. There are other potential dark matter candidates that scientists are considering. One such contender is the hypothetical particle known as the weakly interacting massive particle, or WIMP. Theoretical physicists have also proposed the existence of other exotic particles, such as axions and sterile neutrinos, which might be the constituents of dark matter. Each of these candidates comes with its own set of challenges and unanswered questions. For example, despite extensive searches, we have yet to detect WIMPs directly. Similarly, while axions and sterile neutrinos have some attractive features, their existence remains purely theoretical at this point. Closing. Despite these challenges, the search for dark matter continues, and new discoveries are always on the horizon. The quest to unravel the mystery of dark matter is not just about finding the missing mass of the universe, but it's also about deepening our understanding of the universe and its fundamental laws. So let's keep watching this space. Who knows what we might discover next? The quest to unveil the true nature of dark matter is far from over, and the primordial black hole hypothesis presents an exciting direction. Researchers around the globe are tirelessly working, using cutting-edge technology and innovative methodologies to test this compelling theory. Observational campaigns are in full swing, hunting for the telltale signs of gravitational microlensing that could confirm the existence of primordial black holes. In tandem, astrophysicists are meticulously studying the cosmic microwave background, looking for the subtle imprints that these ancient entities could have left behind. In the theoretical realm, physicists are grappling with the daunting mathematical and conceptual challenges posed by this hypothesis. They're working to reconcile it with our current understanding of astrophysical phenomena and to explore its implications for the structure and evolution of the universe. If dark matter is indeed composed of primordial black holes, it would revolutionize our understanding of cosmology. It could potentially solve the puzzle of dark matter and shed light on the mysterious early epochs of the universe. It could also have intriguing implications for the nature of black holes and the fundamental laws of physics. But the road ahead is not without obstacles. The primordial black hole hypothesis must stand the test of rigorous scientific scrutiny and overcome significant observational and theoretical hurdles. It's a thrilling scientific journey, filled with the promise of discovery and the thrill of the unknown. In the grand scheme of things, these endeavors don't just reflect our curiosity about the cosmos. They're a testament to our relentless pursuit of knowledge, our determination to solve the universe's most profound mysteries, and our insatiable desire to understand our place in the cosmic tapestry. As we continue to explore the cosmic depths, who knows what secrets we might uncover about the universe and our place within it.